In this video, I am going to share with you the working of a tunnel diode. Before that, let us have introduction with a tunnel diode. What is a tunnel diode? It is nothing but a highly doped semiconductor diode that conducts current by quantum mechanical tunneling of electrons. The impurity concentration is adjusted about 10 raised to power 18 impurity atoms per centimeter cube. It is used as a very fast switching device in computers, in high frequency oscillators, and also in amplifiers. It can be switched on or off in about 1 nanosecond. A tunnel diode is also known as B.Sc diode after the name of Japanese scientist who also got Nobel Prize for this invention. Now let us have a look on volt ampere characteristic curve of a tunnel diode. A considerable amount of current flows through the tunnel diode when it is forward biased or reverse biased, as shown in this figure. The forward current acquires a peak value at a particular voltage denoted by V with subscript P, and then it starts decreasing with increase in voltage beyond Vp. The forward current reaches its minimum value at another particular voltage called valley point voltage, V with subscript V, and again it starts increasing in a manner similar to that of an ordinary PN junction diode. Now, to explain the working of tunnel diode or to explain this volt ampere characteristic curve, we will have to recall the energy band diagram of an ordinary PN junction diode. This is energy band diagram of an ordinary semiconductor diode. In this case, in this diagram, dots represent free electrons and small circles are representing holes. It is clear that Fermi level has the same value on both the sides throughout the body of diode. Here, V naught represents height of potential barrier at the junction. Now, let us see what is the shape of energy band diagram in case of tunnel diode. When tunnel diode is unbiased, the energy band diagram is as shown in this slide. In case of tunnel diode, due to very high doping concentration, the value of V naught, that is height of potential barrier, is very high, and width of depletion layer becomes very small. Also, due to high concentration of impurity atoms, the acceptor level on P side gets converted into acceptor band and donor level on N side converts into donor band. As a result of this, the acceptor band overlaps valence band on P side and Fermi level EFP gets shifted inside the valence band. Similarly, on the N side, the donor band overlaps conduction band and Fermi level EFN gets shifted inside the conduction band. It should be noted that Fermi level in this case also has same energy value throughout the body of tunnel diode. When tunnel diode is unbiased, that is when value of applied potential difference V is equal to 0, then there is no scope of conduction current through PN junction, that is current is 0 for 0 potential difference. This explains point O in volt ampere characteristic curve. When tunnel diode is slightly forward biased, that is when applied potential difference is less than Vp, then height of potential barriers starts decreasing and energy bands start crossing each other. Even now, the height of potential barrier is so large that free electrons from n side can't jump over to p side. The presence of forward current in this region can be explained by the process of quantum mechanical tunneling, for which following two conditions must be satisfied. Number 1, the filled states on n side should be in the same site as the site of empty states on p side. Second condition is a strong electric field should be present to suck the electrons from n side to p side through p-n junction. In this situation, both these conditions are satisfied and electrons can tunnel through the junction. This gives rise to forward current. As the forward voltage is increased, V0 decreases further and more electrons on n side come in front of holes on p side. This gives rise to increase in number of electrons that can tunnel through the junction. As a result, forward current goes on increasing with increase in forward voltage. This diagram explains volt-ampere characteristic curve from point O to point A in the graph. In this way, when we go on increasing the forward voltage, then a stage comes when both the bands come exactly in front of each other, and in this situation, maximum number of electrons tunnel through the junction. This corresponds to the peak in volt-ampere graph corresponding to voltage Vp as shown in this figure. On further increasing forward voltage beyond the voltage corresponding to peak, the height of potential barrier reduces further and bands again start crossing each other. As a result, lesser and lesser number of electrons come in the site of holes. This gives rise to decrease in the value of current with increase in voltage. The current becomes minimum when the bands completely cross each other, as shown in the next slide. When voltage becomes equal to corresponding to valley in volt-ampere characteristic curve, in this situation, the conditions of quantum mechanical tunneling are not satisfied, and theoretically it is expected that current value should be 0. But the graph shows that even at valley voltage, current does not have 0 value. This excess current is due to tunneling of valence band electrons of n side, which are available due to breakage of some covalent bonds. By further increasing the forward voltage beyond valley, the height of potential barrier decreases to such an extent that free electrons on n side can jump over the barrier and give rise to diffusion current by recombination of electrons with holes on p side. Thus, tunnel diode starts behaving like ordinary p-n junction diode beyond valley voltage. With increase in voltage beyond valley voltage, more and more electrons on n side are able to jump over the potential barrier and giving rise to forward current. Now let us come to the situation when tunnel diode is reverse biased. When tunnel diode is reverse biased, the bands having filled states on n side and bands having empty states on p side start crossing in opposite direction. The height of potential barrier increases and there is no chance of current due to majority charge carriers. The reverse current is due to quantum mechanical tunneling of minority charge carriers, that is free electrons from p side to n side. As the reverse voltage is further increased, more and more covalent bonds break and reverse current goes on increasing. Thanks a lot. I expect comments from the viewers and I will try to respond to those comments also.